And I would like to thank you all for having the intellectual curiosity to show up on a Friday night to hear a college professor talk about subjects that neither he nor anyone else fully understands. I think it was Bismarck who said that a journalist is someone who is in the business of explaining to others what he himself does not understand. And I seem to have picked a subject that will guarantee that I maintain that tradition. Now, can I come out here and y'all can still hear me? Okay, that's good, because in addition to these other caveats I've been mentioning, I don't have my speech. So I'm hoping I'm going to find it over here. Otherwise, we'll go right to questions. My fellow Americans. No, it's not that one. Here it is. Mind and universe appears to be the subject of this speech. Well, we're in the universe, that much I'm sure of. The Big Bang happened here, right here. Equally everywhere. Didn't happen somewhere else. Everything that we're made of, everything we ever touched, experienced, everything around us tonight is part of that original event. We're in the universe. And my talk tonight has to do with the question of who we are and what the universe is like, how it works. Now, I don't know about you, but in my experience, when I go to a lecture, it's kind of a, since I'm not a regular churchgoer, it's become sort of a substitute for going to church. By which I mean that I tend to listen to the beginning of the sermon and then my mind kind of wanders. Now that's all right, as Stuart Smalley would say. That's all right. So that's what you feel, you know. You don't have to pay attention to every word. For the aid of those of you who will be contemplating your lives, your futures, or your problems and triumphs during the next 40 minutes. So after all, I'm the only person in the room that actually doesn't get to do that. Let me go right to my philosophical point so that I'll make my argumentative point here, and then all the rest is just going to be factual stuff that's supposed to convince you of the rectitude of this point. And that point is that reality is dialogue. That there's no such thing as an object independent of potential observation of it, nor is there any such thing as a mind independent of the act of perception, of observation. In other words, to borrow from Aristotle and many others, entities are inherently interdependent. It's pointless from this view to imagine space, for instance, existing in the absence of objects, by virtue of which the dimensions of space might be measured. Aristotle, by the way, made a very nice argument like this as to why there was no space outside of the outer sphere of his spherical Earth-centered universe, and he made it better than I would, but I recommend that you read his words on that. The same, it seems to me, is true of time. Absent a phenomenon by which to measure its passage, more than one, in fact, the concept of time vanishes. Similarly, it's difficult to imagine a mind, a lonely, singular mind, absent any sense data, no light, no sound, nothing to touch or taste. Or a universe with no observers ever. I don't mean by this to assert that it's all in the mind, that nothing out there exists, that it's just ourselves, or oneself. I think it was, wasn't Bertrand Russell was supposed to have been approached after a talk by a solipsist who said, he'd said something sympathetic to solipsism, which is the belief that no one else in the universe exists. And she said, I can't tell you what a relief it is to meet another solipsist. So I'm not trying to make assertions about existence. I'm just saying that conceptually, It seems to me that it's a dialogue, a relationship, and that some sort of dialogue or relationship is inherent to the concept of mind and universe. I'll read you a little passage about this from my book, The Mind's Sky. I envision our relationship to the universe as hourglass-shaped. On one side is the outer realm, inhabited by galaxies, stars, the plants and animals, and our fellow human beings. Most of us, the solipsists aside, believe that this outer world exists, though we appreciate that our direct perceptions of it are limited and skewed. On the other side is the inner realm of the mind, where each of us is destined to live and die. Here resides all we can ever know. We would feel as trapped behind our eyes as an animal behind bars, were we not able to keep expanding the inner realm by means of learning and contemplation, and one might add, an imagination. Through the neck of the glass flow all the sense data by which we perceive the outer realm, and, flowing the other way, the models and concepts that we apply to nature. We tip this imaginary hourglass from time to time. In the 19th century, when classical physics ruled, we tended to think of the sand as flowing almost entirely from the outer world to the inner realm, from an objectively real world to our passively recording minds. In the 20th century, the concept of observer-dependent phenomena in quantum physics has shifted our attention to the ways that our observations influence how we perceive nature. But so long as there are thinking beings in the universe, neither bulb of the glass will ever be entirely empty. Now, tonight I'd like to investigate this relationship, and I'd like to focus on 3 points. First, what do we know about the universe and what makes us think that this knowledge is accurate? Second, why do we think it's a universe, a cosmos, one thing and not many things? And third, why do we think the same about the mind? Why is a sane individual said to be of one mind and not of many minds? Now that ends the thesis, so those of you who want to drift off now have my blessing in doing so. And for the rest of you, I'm going to start with a state-of-the-art graphic aid here. Oh, it's already there. I was afraid I'd lost that too. And to confirm the academic nature of the talk, I brought with me a pointer. You paying attention now? 3 facts that we think we know about the universe. It's expanding, it's evolving, it's all made of the same stuff, obeying the same physical laws. There'll be a quiz on this later. So I'll leave it up there so you can commit it to memory. Meantime, I want to say a little about each of these points. What we mean by to say that the universe is expanding is really involves my trying to get across 2 concepts, which I hope won't be entirely unfamiliar. One is the expansion of space, and the other is the curvature of space. By the expansion of the universe, we mean that the space between the galaxies is stretching out, is itself expanding. This, in turn, means 2 other things. You have to just keep track whether we get back through all these branchings or not. It means that it's the expansion of the universe is taking place out there between galaxies, indeed between clusters of galaxies, and not locally. As Woody Allen was reassured in his boyhood, Brooklyn isn't expanding. It's space that's expanding. And secondly, the expansion is not a case of objects expanding in a pre-existing space, rather it is the space itself that's expanding. And this is a concept that has to be gotten clear if one is not to get confused. The expansion of the universe is not a case of things, let's say galaxies, being hurled out through a pre-existing space. All the space was in there all the time. The space we've got around us was in the Big Bang. We didn't sort of get here from someplace else. But that space, the metric as they call it, is expanding all the time. Now, what makes us think that this is the case? Actually, nobody did think it was the case until evidence for it was discovered. Einstein wrote a theory, general relativity, that he thought produced a static universe. And he was happy about that because all the data indicated the universe was static. It turned out the theory wouldn't do that. It was a mathematical error on Einstein's part. Relativity demands a dynamic cosmos. It must be expanding or contracting. In other words, the theory says to you, if the universe is constructed in this way, out of curved space-time, it can't be stable. Einstein tried to fix the theory to make the universe stand still. It didn't work. Around that time, astronomers who knew nothing about relativity, found it as incomprehensible as most of us do today, discovered that the universe really was expanding. Astonishing confirmation of theory by observation. Well, this is what's called the Hubble Diagram. It's the basic diagram that indicates the expansion of the universe. Across the bottom here is magnitude, and this is roughly equivalent to distance away. That is, the further away you look, going in this direction, toward the higher numbers, the more distant each galaxy is. Now, galaxies vary in their brightness, so that causes a lot of scatter, but further away, the dimmer they are. This is redshift, meaning a shift in the spectral lines of the galaxies toward the red, which is the only consistent explanation for which that's ever been found is that it's a Doppler shift. It's the same as a car horn, the car is speeding away from you. An object moving away will show a red shift in its spectrum. And that red shift increases as we look at galaxies further away, and that's the Hubble law. Now, as to the curvature of space, I have a few diagrams that I've prepared using my own artistic ability. And this says that if one star can bend light, which relativity predicts and which observations conclude, that is to say, any object with mass will bend the space-time continuum in its vicinity, and the way you can see that is that a light beam going by will be bent. Then maybe all the stars in the universe could wrap up the whole universe in light beams, which is to say, could wrap it up in its own curved space-time continuum. This would be a spherical universe, and it's one possible way the universe might be. We don't know the actual shape of the universe yet, but it might be akin to a four-dimensional spherical shape. Now, such a universe of curved space has one great drawback, and that is that human beings can't imagine it. So I urge you not to go home and try to imagine it, because you can't. But it also has one wonderful property, and that is that it solves the ancient paradox of whether there's an edge to the universe. And people were thinking about this back in times of the ancient Chinese and the ancient Romans. Lucretius wrote a great statement of this paradox. Is there an edge to the universe? If you say that there is, then imagine that you go to that edge, he said, and hurl a swift spear. Oh, here, I have one. Hurl a swift spear past the edge. Where does it go? Does it bounce back? Then what's it bouncing off? If you think that there is no edge, then it goes on forever and introduces all sorts of problems of infinity. And those are serious problems. The same sort of thing occurred with the flat Earth cosmology. A two-dimensional world, if it's going to be finite, has to be bounded. That was the origin of the superstitious belief that you could fall off the edge of the Earth. A belief not widely held in the days of Columbus, by the way. It is resolved by imagining the world to be three-dimensional, by adding a dimension. The surface of the world is then finite, but it is unbounded. You can travel indefinitely in any direction on the surface, and you'll never reach an edge. Similarly, a universe of curved space-time, let's say spherical in shape, for sake of example, permits a beam of light to travel indefinitely in any direction, never reach an edge. So it's unbounded, and yet it can be finite in size. Now, if we continue this model, imagining the universe to be like the Earth, and introduce expansion, then we have an expanding Earth model for the expanding universe. Suppose that the Earth were expanding, and we discovered this fact by making observations of other cities. let's say the Earth got doubled in size every hour. So if you looked at a city that was only 100 miles away from you, a little town, in an hour it would move 100 miles further away, so its velocity would be 100 miles an hour. Look at a city 1,000 miles away, its distance would also double, so it would have a velocity of 1,000 miles an hour. In other words, you would have a law which was that the further away a city was, the faster you saw it receding from you. And notice every other observer would see it receding as well. And that is the Hubble relation. Galaxies, further away they are, the faster they're seen to recede. So that's what's meant by expansion, and it contains these two concepts of the stretching of space and of the curvature of space, or more properly, the curvature of the space-time continuum. Now, as I say, it's hard to visualize, but I find that rewarding, in fact. I would be suspicious of a cosmology that didn't require that we go beyond concepts that, after all, evolved here on an earthly setting. J.B.S. Haldane said, "The universe is not only queerer than we suppose, it's queerer than we can suppose." So that's my first point, is that we think the universe is expanding. This is some of the reason, and not all of it, that we think that's the case. Secondly, we think it's evolving, and I'm going to move more quickly over this point. I'll give you a definition of terms here, and you get two definitions for the price of one. Here I'll throw in universe. By evolution, we just mean that complexity and a variety of phenomena are increasing in a given system over time. One way to talk about the expansion of the universe is to say that the matter density, that is, the number of atoms that are found in an average quart bottle's worth of space, let's say, in the universe, is decreasing as time goes on. So the same number of atoms, but the space is stretching out, so things are thinning out, generally speaking. Not in Brooklyn, not here, but on the cosmic scale of things. If you run the clock backward, you see the density going up, and this implies that the density was quite high at the beginning. Generally speaking, very high density environments in nature are characterized by high energy as well, because whatever level of vibration of particles you have, if you jam them together, they're bumping into each other. Sort of like the difference between living on a farm or being in a subway car. The energy level goes up. If so, the early universe was different from the universe today. During the first second of time, for instance, virtually no structures in nature as we know them today could have existed. The most highly developed particles would have been, say, the quarks, which have very little internal structure, basically basically none as far as we know. As time passed and the universe cooled, it would have become possible for subatomic particles to form made of quarks, like protons and neutrons. And then as time passed further, around about several 100,000 years, it would be possible for these atomic nuclei to be joined by electrons and form stable atoms. This process, in some sense, has continued ever since to implicate the evolution of stars and planets, of chemistry on planets, of life and thought. So it becomes possible to write a history of the universe, and here's a brief version of it. A lot of science has been devoted lately to trying to sum up this story of cosmic evolution from early times to later. From the standpoint of high-energy physics, most of the interesting stuff happened during the first second. Somehow space and time originated, perhaps by some higher dimensional space, to use that term. Suspiciously enough, the favorite is 10, collapsing to the 3 + 1 dimensions that we find today. And this is a fascinating subject of symmetry breaking, which I won't go into tonight, but it's an amazing part of science. This is also during this first second that the epoch of cosmic inflation is thought to have occurred when there was a period of very rapid expansion, flattening out space-time, making the universe much larger than had been thought. 4 forces of nature that we find today may have originated in a single force, which may go back to this business of higher dimensionality. Then, in here somewhere, leading up to 3.5 minutes or so, the nuclei of atoms congeal. Around 10 to the 6th years in round numbers, the atoms get organized, and that makes the universe transparent. That's an important point because that's when all the photons that are generated in these particle interactions suddenly get released to fly through space ever after, creating what we call the cosmic background radiation, the microwave background. I'll say more about that in just a second. Somewhere around 1 billion years, galaxies and stars are thought to form. And by this point, the physicists lose interest, but all the great achievements of human society occur much later. Now, if the story has gone as I've been stating it, back when those photons were released, they should have created for all observers a kind of just a background energy level, and the expansion of space ever since would have stretched out those photons from the wavelengths of light down to the longer wavelengths that we call microwave radio. And theory physics makes very specific predictions about what this radiation ought to look like. First, it says it ought to exist, and indeed its existence was discovered by radio astronomers who had never heard of the theoretical prediction. They were just testing a radio antenna when they discovered it. Secondly, the theory predicts that the background radiation should obey a certain spectrum, what's known as a Blackbody Curve. I want to show you one of the most amazing pieces of sets of data, I think, in all of observational science. The curve here, the unbroken line, is the theoretical prediction of the spectrum that should be obeyed by the cosmic microwave background radiation, this glow coming from all directions and dating from when the universe was less than 1 million years old, from the release of those photons in early time. The cosmic background observer, the COBE satellite, was launched to get above the atmosphere, which screens out some of these wavelengths, and give us our first clear view of the entire spectrum. These boxes are the actual measurements made by the COBE satellite. Now that's not bad confirmation of the theorem. That purports to tell you something about the early days of the entire universe. The theory also predicts that this radiation should be smooth all over the sky. It should have about the same temperature in all directions, except for a small hot spot in one side of the sky caused by the proper motion of our galaxy and our solar system and so on, and a cold spot on the other side. And these have to do with our motion relative to the overall cosmic frame, what's called the Machian frame of the universe after Ernst Mach. But the theory says it shouldn't be too smooth, because if galaxies got formed in the first billion years, as we think, then traces of that structure should have been present in the primordial matter, even when the background radiation photons were released. So you ought to see it at a low level, some trace. Theory predicted that you'd find that trace somewhere as you approached 10 to the minus 6th difference between the coolest and the hottest parts. Very subtle difference, and COBE worked away for years on it. And as you know from reading the newspapers earlier this year, finally produced signs of structure in the background radiation. These things are enormous fluctuations, areas where the density changes in the early universe. And this is not the universe expanding into something here. This is just a sky. It's just a way of showing you the sky, you know. You're looking out on the sky and you're seeing these things. Now, these are very large. In fact, they are larger than the observable universe was at that time. And the only known origin for such structure are quantum flux events that would have occurred early in the Big Bang, when the universe was a particle physics universe. So we have confirmation here of a whole range of theories, including what are called gravitational instability pictures, and the Big Bang Theory itself. This does not mean that we sort of have cosmology wrapped up by any means. It does mean, though, it seems to me, that within the great arena of the Big Bang Theory, at least, science is moving in a promising direction. And there's a lot to be worked out even within the parameters of this theory. Okay, so that's a Big Bang précis. Now let me show you a few pretty pictures about having to do with the actual universe, which after all is out there. So if we could turn the lights down a bit, I'll see if you can make out some of these. The wonderful thing about astronomy, you know, is that it is all out there. So you don't have to take my word for it that the Milky Way has a companion galaxy called the Andromeda Galaxy. You can haul a telescope or a pair of binoculars out in your backyard this time of year and look up and find it. You know, it's accessible to observation. This is an X-ray image of the sun. The sun is a star, and stars all burn by releasing some of the energy, just a little bit of it, that is pent up in the nuclei of atoms. Why is there energy in the nuclei of atoms? Because in some sense, all of matter is just congealed energy. And if you heat it up, you can release some of that energy again, turn it into a fluid form, in this case a plasma form. In other words, why is it congealed? Because the universe has cooled off. Things have frozen out. Now, one test of the Big Bang Theory is chronology. Try to get a sense of the age of things. If you estimate how much stuff is in the sun, what can all the brightest nuclear physicists tell us about how the sun works? How long should the sun have been around, if that's the case? The answer is about 4.5, 5 billion years. The universe as a whole, according to the Big Bang Theory, is maybe 15, 20 billion years old. So the sun should have come along in the last quarter or third of cosmic time up to the present. If that's true, the theory predicts the sun should have a certain composition, which is to say that it should have more heavy elements in it than younger stars do because they were brewed up in stars. Sure enough, it does. The theory is correct. It should also be able to make some determinations about the ages of planets, like this one. This is the Earth. So we got it on its side here. It's very important with the Earth to have it right side up. By radioactive dating of materials on the Earth, you can find out how old the Earth is. And the answer comes in something like 4.5 billion years. A little younger than the sun, is about what you would expect. Then you'd like to go and look around at other planets. Start with the moon. Here's a lunar excursion module going down to the surface of the moon. Gather up samples of moon rocks and bring them back, and one reason is to age date the moon. The moon turns out to be about the same age as the Earth, formed about the same time. And you can learn a lot about the history of the moon, too, which is a subject for another lecture, but an interesting one. This picture, before I leave it, by the way, this particular mission was designed to land in a crater near the Surveyor, an unmanned craft that had been set down on the moon years earlier. The idea was the astronauts would, if they landed close enough, they would make their way across the lunar landscape to the Surveyor, saw a piece of it off, and bring it back to Earth so that the metals could be analyzed to see what things like how much cosmic ray flux had influenced it. The LEM went down under computer control, and the navigation was so good that the astronauts were alarmed to discover at the last moment that unless they took over, they were going to hit the Surveyor. You know, these things are more common than people think. I believe it was in the year 1896, there were only 2 automobiles registered in Kansas City, Missouri, and on the 4th of July, they collided. When we move out further from the sun, we encounter the gas giant planets like Saturn. These planets are gas giants, that is a lot of cold gas around a rocky core, because they formed far enough from the sun that the brilliant sunlight of the young star in the early days did not blow all of that gas away. So as we come to understand how the solar system formed, we can realize that the composition of the planets is not just something given to us, but tells a story about the evolution of our part of the universe. Similarly is the geological story of Mars. This is the largest volcano in the known universe. It's on the planet Mars. How come it's so big? Mars itself is a small planet. Answer, Mars does not appear to be geologically active anymore. It has no plate tectonics, so when you make a volcano, the volcano just stays there. It doesn't walk away from the hot spot as it does on Earth, so it just keeps building and building. You get big volcanoes. All this happened long ago when Mars was a planet with running water, warmer climate, volcanic activity, and something dreadful happened and it all stopped. It's been pretty desolate there ever since. It might be in our interest to know what that was. Triton, the moon of Neptune, coldest place in the known solar system, takes us into the outer part of the solar system where you start to encounter pristine materials like this. Here's a comet. These are of interest because they contain material that hasn't really changed much since the solar system was born. So it helps get the composition of the original solar nebula, which in turn ought to be able to tell us how it came to be that the sun and planets got triggered into formation in a particular time and place. So I want to show you a few of these solar system slides just to make the point that space missions and all that aren't just about going out and seeing how things look or making pictures of comets and all. They're about trying to piece together the story of cosmic evolution. And we ourselves are a result of that story. There's nowhere I've been able to find in the whole history of the universe that you can insert a knife blade and say, okay, everything that happened before this point had to do with nature and physics and, cold stuff that they teach in science class. But after that, it all had to do with the miracle of life and fuzzy animals and composing, Bach's music and stuff like that. There is no such place. It's all a continuum. We're in it. We can be ignorant of it if we like, but we owe our lives to it nonetheless. Now, the rest of the pictures I'm going to show you take us out into interstellar and then intergalactic space. This is a picture along the Milky Way, and what I want to draw your attention to is all this dark material. This stuff is not space. It's dark clouds silhouetted against background light. This, in fact, is part of the plane of our galaxy, and it's, of course, what you see in the sky as the Milky Way. We're in a fertile, star-producing galaxy, and this is the stuff out of which it is busy making new stars. Here's a close-up of one part of one of those dark clouds, and this is an active star-forming region, and you can see there's dark material from which some of these brilliant, giant new stars are being formed. The mechanism for forming a star is a subtle one. It includes a shock wave moving through that disk of the galaxy and compressing material so that gravity can take over and form stars and planets. And then, before I tell you the rest of that story, let me show you a picture of a rich star field. It's a very efficient process. It makes a lot of stars, a few 100 billion of them in this galaxy alone, and here you can see a dark area silhouetted against it. Stars tend to be born in clusters, and here's a young star cluster near the sun. Now, when you make a bunch of stars this way, using this recipe, you get them in all sizes. You make probably a lot of objects that aren't big enough to become stars. They never fire up nuclear fusion at the core. And you make the whole spectrum up, normal-sized stars like the sun, on up to giant and what are called supergiant stars. Now, these really big stars burn their fuel so fast that they don't last very long. It's sort of counterintuitive. You'd think a giant star was going to last a long time, but the rate of burning goes up by the cube of the mass. And so a really massive star does not last long at all. A comfortable, pedestrian, sensible star like the sun is good for 10 billion years. May not make much of an impression. If we went to the very nearest star and looked back at the sun, it would be so dim that you'd have to be a well-versed amateur astronomer even to know the name of it. because I don't know what they call it. But it lasts a long time. Supergiant stars are splashy. They make a lot of light. But they have lifetimes measured in only like 10 million to 100 million years. No time at all in the cosmic scheme of things. Then they blow up. And this is a picture of one blowing up in the neighboring galaxy, the Large Magellanic Cloud, back in 1987. Here's the detonating star, and you can see it is still tangled in the large star-forming region, actually the largest one we know, Tarantula Nebula, from which it was born. Like most supernovae, it wasn't around long enough even to drift away from its birthplace. It went through its whole spectacular career and blew up right in its old hometown. Now, what's interesting about this is that the force of an explosion like this sends a tremendous amount of material flying out from the star itself and material that piles up from the dense surrounding medium. And this is a picture of an area where this has happened. And this is part of a big bubble of gas being thrown off by one of these supernovae, by these exploding stars. That explosion, in turn, by stacking up material, triggers the formation of further stars, so that star-forming regions are largely fueled by their own supernovae. And we believe, on evidence from chemical abundances here on Earth, that that is how the Sun and its planets came into existence. We weren't one of the first stars formed when the shock wave came through in our neighborhood, but we were formed soon after by the detonation of a supergiant star in our neighborhood. Now I want to look at some galaxies. This is an irregular galaxy, one kind of galaxy that you find as you get out past all these stars in our own galaxy, and the foreground stars are in the Milky Way. It's just a kind of a spherical aggregation of stars. Then we have spiral galaxies, which is like the one we're in. Here's a pretty spiral galaxy. And what we see as the spiral arms are, in fact, those density wave patterns that have set off star formation. Lots of star-forming regions are glowing in there, bright giant stars, and that's what gives you the appearance of the arms. So the arms aren't objects, they are phenomena. They're like the glow of plankton that you see on an ocean wave at night. There aren't any more stars there than in the rest of the disk. It's just fireworks passing through. When you look at spiral galaxies edge on, you can see how they contain in their disks that dark gas that we saw in our own Milky Way. And this is a particularly dusty galaxy. Plenty of material to recirculate into new stars. Now, as astronomers have been studying galaxies, they've found that there are galaxies, too, have to be right side up. I was down at this Cerro Tololo Observatory in Chile with Alan Sandage, great galaxy astronomer, and he handed me a plate of a galaxy, and I held it up, and it was upside down, so I laboriously turned the big glass plate over, and he started to make fun of me, and then he paused, and he said, well, actually, to tell you the truth, I can't look at them upside down either. There's only one right way, Astronomers are beginning to realize that what goes on in a galaxy is determined not only by all these processes we've been talking about inside, but also by interactions between galaxies. Most galaxies are gravitationally bound to other galaxies. That makes them proof against the expansion of the universe. They'll go on for the indefinite future together. Most spiral galaxies are found in pairs, binaries rotating in complementary directions, apparently forming out of adjacent eddies in the primordial material. And our Milky Way is in such a pair. Typically in such a pair you find one galaxy, rather like a crab claw, is about twice the size of the other one, and that's the case with our pair. We're the small one, this is the big one, Andromeda spiral. You also find satellite galaxies orbiting the big ones, and that's what these two are, satellites. And they are typically irregular looking, and that's because the tidal interaction with the big galaxy keeps disturbing them and makes it hard for them to keep a coherent shape. These interactions are important in studying the evolution and ecology of the universe because they have dramatic effects on the galaxies involved. Here are two galaxies interacting. A lot of stars are actually being pulled away from the big one toward the little one and vice versa. Some stars are just being blown off into space. That would make astronomy difficult. I often wonder if we were in such a situation, it would be hard to apply what's called the Cosmological Principle, which is the assumption that one's location is typical. You want to have such an assumption because otherwise you can have any number of theories. You can always say, well, we're in the center of the universe. That's how we started out, you know. That's why it looks like we're in the center. It's not a very good argument because only one planet gets to be in the center, you know, in such a model. And so it's sort of special pleading. If the sun had been hurled out of an interaction like this 100 million years or so ago, and we come along, we evolve on the scene, we look out, there are no stars in the sky. The whole universe is made of galaxies. Everybody else has a starry sky except us. We'd have to evolve the cosmology that determined how it was that we'd gotten to be orphaned. Meantime, these galaxies would have moved on. It would be kind of hard to tell how we'd come to be in that situation. Sometimes when galaxies interact, they merge. This is a merger of two large galaxies in a nearby group. There's a spiral in there, apparently in the process of being eaten by a giant elliptical galaxy. Nobody gets hurt in these encounters. They take a long time. There are few, if any, stellar collisions. But I point them out to you. Here's a group of galaxies interacting to make the point that two things are going on. The universe is expanding, thinning out globally, and yet locally galaxies are consolidating, interacting. Fancy chemistry is taking place. Life and thought is coming into being on this planet and very possibly on others as well. And these influences, again, can be traced up. You start on the planet and you keep going up, and you can't seem to find any particular point at which you can say, well, this is no longer local, it's cosmic. Here's a cluster of galaxies, and you start to see structure in these clusters with certain kinds of galaxies, more ellipticals toward the center and spirals toward the outer parts. So however the galaxies formed, it seems that they formed as clusters or superclusters in large units. And I'd like to conclude with just a couple of shots having to do with the constancy of physical law over time. This is a jet in a nearby galaxy. It's a hunk of plasma that's being spat out from the center of that galaxy, probably by a supermassive black hole, at almost the speed of light. It's moving just about as fast as you can get anything to move from a standing star. And it's moving so fast that it's generating all kinds of energy as it goes through the intergalactic medium around it, including an intense blue light. These jets are very interesting and high energy. They're kind of rare in the current universe. But when you look far away, and therefore back in time to when the universe was younger, you see them a lot. This is a quasar toward the outskirts of the observable universe. Billions of years ago, there were a lot of quasars. And when you look at some of them closely, what do you find? Just the same kind of high-energy jet. This is one of many kinds of evidence, spectroscopic and otherwise, gravitational, that indicates that there are such things as laws of nature, and they do hold across the vastness of cosmic space and time. I'll show you in our last concluding slides here a model of the nucleus of an atom. We made this on 3 VAX computers in 3 different cities. And there's a lot going on in here. It's a part of a motion picture sequence. Inside each of these nuclear particles is 3 quarks, and they're exchanging gluons, and all this wonderful structure is going on. Every one of these nuclei of a given element, simple hydrogen, helium in this case, so on, is identical all through the universe. They all trace their lineage back to some common event at the beginning of time. The very existence of this kind of continuity is an argument for the Big Bang theory. Well, so I'm just going to leave behind the astronomy side of the talk with this comment to remind us that we are in it, and it's not just just out there. Okay, if we could turn the lights back up at the risk of awakening anyone. I want to conclude by turning attention to the other side of the equation, and that is the mind, the other side of the hourglass. What we might envision as the difference between the roots of trees and the branches. The root system perhaps representing the perceiving mind, any mind, not necessarily human, and the branches, the observed universe. Again, a kind of a symmetry and traffic back and forth between the two. When I wrote about that in my most recent book, I called some tree experts to find out if it was true, as I'd been taught in school, that trees could have root systems just as extensive as the branches. It was important to the symmetry of my argument to say this. And they said, well, we don't know, actually. There's almost no literature on root systems. So I went and looked, and sure enough, they were right. And the reason is it's too hard to dig them out. You know, they're so articulated. And there was one paper in all the literature that I looked at that had a real photo of a root system. It was by some poor soul who had laboriously washed out a whole hillside to expose these roots and then painted them white, you know, and taken a picture of them. Well, there were a lot of them, so I relied on that. And I said, okay, yeah, that's the same as them. Now, we've seen that the universe, although it contains many different things, is in some sense one thing, a cosmos, a unified system. And the same seems to be true of the brain. The brain is made up of many parts, and yet we think of ourselves as being of one mind. So I want to take a moment and take a look at the brain. Anatomically, the brain is clearly made of different parts that have been built up over time. They have different anatomical ages. This is just a classic cutaway. The lowest part of the brain, one model we can use, what's called the triune brain, three-part brain paradigm. The lowest part of the brain is the oldest part and the part that we share with the widest number of other creatures. It's the part of the brain responsible for aggression, territoriality, and ritual. Sort of explains why you so often find those together. Above it is the limbic system, the seat of powerful emotions, a sexual instinct, and the sense of smell. Another trilogy often found together. This is why, for instance, perfume is useful for love but not war. And then way up top there, the cortex and neocortex capable of abstractions such as language and geometry. That's where logic takes place and rationality, and the fact that it's been added so late to the brain may suggest why it is that people aren't more rational. You know, as a computer scientist at MIT said, the trouble with logic is it doesn't work in the real world. If you're in, let's say, a political campaign, you can't very well argue that something your opponent said was not rational. That does not earn you any votes. Rationality has very strict limits. But the neocortex is important anyway, even if it's just that outer layer. I was reading today in a novel by Patrick O'Brien, the great naval historian, that in the British Navy, the three most serious crimes for which you were most likely to be flogged or even hanged were mutiny, sodomy, or damaging the paint. You know, they used to paint these ships beautifully, and if you bumped into it with a launch or something and scraped the paintwork, they were really angry about it. And offenses against logic are sort of like that. They're superficial, but they matter. So. Now, the brain also appears to be multiple when it's viewed phenomenologically, that is, without looking anatomically, but just in terms of how it operates. And here I want to, in the few moments remaining, acquaint you with the work of Michael Gazzaniga, a American neurosurgeon, who, this is dyslexic sign there. Now, as you know, the brain is divided in such a way that the left forebrain controls the right side of the body, and the right brain controls the left side of the body. And each eye has a field of view divided into two sides, and the right side of that field of view is controlled by the left side of the body, and the left by the right. In evolutionary terms, by the way, I'm not sure if I believe this argument, but this is supposed to be because in very early creatures, if you were fleeing from something, it was a good idea to have the brain part, the important part, away from the part that was going to get bitten off. So you're just sort of going, yikes, you know. And, well, I lost the right side, but, you know, I'm only a microorganism, so it's not like I won't look my best. In any case, that's the basic division. And as you also may know, work by many neuroscientists has established that there's some localization of function in the brain. For instance, language works mostly in the left side, it's controlled on the left side. Spatial relationships and images on the right side. Right side of my brain's getting a rest at the moment because I can hardly see you. So I have almost no visual information to process. Of any kind, no spatial information. On the other hand, I'm jabbering on and on, so the left side is working a lot. Communication between these two hemispheres is carried on by a mass of connecting tissue called the corpus callosum. It's a wide bandwidth communication channel between the two. If you cut the corpus callosum, you stop virtually all communication between the left and right brains, at least the higher brain. This operation is conducted on a number of people. They're mostly graduate students who didn't know any better and volunteered for it. And were paid $35 and a hot meal each. No, the operation is performed for people who suffer from particularly violent grand mal epilepsy. Because it localizes the seizure in one hemisphere and thus provides considerable relief for these patients. And because of its success, there are now a number of patients who have undergone this operation. Now, interestingly, the effects of the operation are not clear to the patients. Things seem normal to them, and they seem normal to other people. And it takes a fairly sophisticated experiment to start to notice the differences between split-brain patients and others. And this, in fact, is how the specialization of one hemisphere for language, for instance, was discovered. Here's a typical experiment of the kind done by Sperry and his colleagues at Caltech. This is an experimental apparatus in which you flash a word on the screen in a setup in which only half the brain can see it, so only half the visual field sees it. In this case, the visual stimulus is a word. It goes into in this case it's on the left side, so it goes into the right side of the brain, which in most individuals has a rudimentary, at least, language capacity. It has enough to tell what the word means, like bike, a simple word. But it can't tell the left side, which handles speech. So if you ask, well, did you just see anything? The left side responds, no, I didn't see anything. Normally it would have gotten word across the corpus callosum, but the corpus callosum has been cut. So it's in the dark. No, I didn't see anything. However, if you allow the patient to do a drawing with the left hand, for instance, the patient will draw a bike because the right side of the brain is controlling the left hand, and it knows that it saw a bike. It doesn't know how to spell bike, but it can draw you one. And you all remember these kinds of experiments. The part I want to emphasize is Gazzaniga's identification of a center in the brain that he calls the interpreter. It appears to be localized near the speech center in the left brain. And it is a center whose job it is to provide the mind, that is the conscious subject of consciousness, as they say, with a rational explanation of actions. In other words, a coherent, singular explanation, even if it doesn't know the correct explanation. We don't normally see the interpreter in action. We can't tell we're seeing it because normal people have both sides of the brain communicating, but in split brain patients we can. Here's an example from Gazzaniga's book, The Social Brain. A simple command such as walk is flashed to the mute right half brain, and the patient will typically respond by pushing his or her chair back and starting to leave the testing area. When asked where he or she is going, a typical response is, going into my house to get a Coke. The left hemisphere is faced with the task of explaining an overt behavior that was initiated not by that hemisphere, but by the disconnected right brain. Implication, and this is my words now, much of what we think we have decided to do was already decided elsewhere in the multipartite brain. There is, in other words, at least one program among the 100 or more that researchers like Gazzaniga believe the brain is divided up into, one program responsible for maintaining the illusion that the brain is a single entity and that it knows what it's doing. A dramatic example may be found in the phenomenon of posthypnotic suggestion. This is from the Berkeley philosopher John Searle. Under hypnosis, the patient is given a posthypnotic suggestion. You can tell him, for instance, to do some fairly trivial, harmless things, such as, let's say, crawl around on the floor. Must be fun to be a hypnotist. What will I have them do today? Crawl around on the floor or buy a Yugo? You've missed several sessions. Well, it's hard to find a used Yugo. So you plant the suggestion to do a trivial thing, and after the patient comes out of hypnosis, he might be engaging in conversation, sitting, drinking coffee, when suddenly he says something like, "What a fascinating floor in this room," or "I'd like to check out this rug," or "I'm thinking of investing in floor coverings and I'd like to investigate this floor." He then proceeds to crawl around on the floor. Now, the interest in these cases is that the patient always gives some more or less adequate reason for doing so. Always. What's going on? The interpreter, barred by hypnotic command from accessing an accurate explanation of the behavior, makes up a plausible explanation. So I leave to you the question of whether the universe really is unified, or is the mind just so busy being unified that it demands a unified universe. It is a matter of historical fact that we regarded the universe as unified for centuries before we had any evidence that it was so. The word cosmos is a Greek invention. Strangely enough, it does seem to be unified. Does that mean that there's some echo of cosmic unity in the unification programs of the brain? I don't know. It does not, to my mind, mean that we psychologically create the brain, the brain psychologically creates the universe in some subjective sense, and I'd like to just take a moment to dismiss all pop books that make one believe that quantum mechanics or relativity means that science is more subjective. That's not what they're for. Relativity was called by Einstein invariant theory. Its purpose is to make science objective for all observers. So everyone, you and me and somebody flying at 90% the velocity of light toward Andromeda, can all agree that on the fundamental equations of physics. Quantum mechanics, it's true, introduces the observer into the loop. It reveals that the answers we get from observations and experiments are dependent to a considerable degree on the questions that we ask. But that means the question that any experimenter asks. It does not mean that the answer varies depending on whether nature thinks that the questioner is a Republican, Democrat, a Buddhist, or Episcopalian. In both mind and nature, we see illustrated two universal tendencies of nature, one toward variety and the other toward unity. In physics, we've seen that there are only about 100 sorts of atoms, all of them identical, each to each, can yield a fantastic variety of things. For instance, no two planets in the universe are alike. And in life, we see variety, the production of original sorts of individuals leading to new species, and unity, the organization of the varied into functional units like cells, persons, tribes, and nation-states, if they can be regarded as functional. In science, we experience a constant dynamic between these two tendencies. Do we understand the fundamental mechanisms responsible for the evolution of life? Yes, I think we do. Does this mean we understand life itself or why there is life? No. Are we close to writing a unified theory of physics that will shed new light on everything from quarks to galaxies? Yes, possibly so. We might have such a theory by 2000, 2010. Does this mean that we will then have a theory of everything that we'll understand everything? No. The simplest, most rudimentary human behavior, what you're going to do or think in the next second, will remain beyond the range of such a theory and of any foreseeable scientific theory. We're left with the enduring question of whether the universe really is comprehensible or whether the mind simply imagines that it is, and that's what experiments are designed to test. Even Einstein was inconsistent about that. On one occasion he said, the human mind is not capable of grasping the universe. On another he said, more famously, that the most incomprehensible thing about the universe is that it is comprehensible. Both statements can't be right, and yet, in a sense, we know what Einstein meant. He meant that we have a lot to learn. Thank you.
Assuming the expansion of the universe, and assuming that the distant objects are moving faster away than the closer objects, what observations might be made by a person halfway there relative to us?
Exactly the same as are made by us. It's just like if you think again of the surface of the Earth. If you're halfway from here to the other side of the Earth and you look around on an expanding Earth, you'll see exactly the same thing as you saw here.
It's just hard to imagine an Earth expanding and not the objects.
And not what?
It's hard to imagine the Earth's space expanding rather than objects expanding in the space.
Yeah, you can. It might help if you think about, well, what we're really talking about here is a metric for dealing with space. I started out by suggesting that space does not exist independent of measurement of it. You have to find a way to map space. We had Newtonian space was one way of mapping it. Turned out to have many advantages, but some liabilities. The space-time continuum is another and better one. So far as we know, there are no flaws in that as yet, although it does break down, for instance, at black holes. All mapping systems inherently have inexactitudes. A globe, which is the best representation of the Earth, with lines on it, no matter what set of lines you draw for coordinates, all those lines will converge in one set of coordinates at one point. We call that North and South Pole, and for convenience, we set them where the axis of the Earth's rotation is. But if the Earth weren't rotating, you could set them wherever you wanted. You could do it anyway. That point where they all meet is a singularity. It's a flaw in the mapping of the underlying continuum. And all mapping systems have limitations. So it's a question your imagination may be coming up against the unfamiliar or maybe coming up against a limitation of the map. Upstairs at mic 3. None. When I say the stars walk away, that's really I'm sort of putting it backwards. What happens is that the shock wave moves on through, and the stars that form, it's a question where you want to set your frame of reference, but I'll set it on the stars. And from that perspective, it'll look as if the shock wave moves on. The star formation dies out as the material has been used up. The remaining material that hasn't been shocked into stars is blown away into the greater interstellar medium, largely by supernova explosions. The stars? Well, the stars are all orbiting the center of the Milky Way galaxy. So they have a velocity that, in the case of the sun, it takes us about 250 million years to go once around the... No, it's just this is all in one galaxy in the Milky Way, and everything in the Milky Way is orbiting the common center of gravity. Yes?
You mentioned the question of Lucretius throwing the spear at the edge. Similarly, the theory of the Big Bang raises the same question. What was before it?
In terms of time, yes, the Big Bang is the north pole of space-time. That is, that's where the singularity occurs. All the lines converge. Time as we know it doesn't exist before the Big Bang. So one, naturally, the human mind being what it is, one asks, well, isn't there some better paradigm within which the Big Bang can be mapped and its predecessors somehow guessed at? And that may be possible. There certainly are some theories about that. Mike 3. I don't really know. I do recall reading a book called A Child's History of the World by an English author named V.M. Hillier. He's a headmaster, I believe, of a boys' school in England. And it began with the origin of the Earth and a theory that we don't now think is correct. But I was just astonished to realize that the Earth hadn't always been here. And moreover, that the stuff the Earth was made of had been out there among the stars. In fact, it had been stars. Virtually every atom in your body and mine had been processed through an average of 2 stars before it got here in its career. I never have quite gotten over that. So I got real interested in the stars, and I got a little telescope, tried to have a look. Oh, microphone 2 finally has an adherent, yes.
What is the thinking about where the matter from the Big Bang came from, and what is beyond the edge of the known universe? 2 simple questions.
Well, there's a lot of thinking. I don't know how much use it is. The matter's not a problem. Oddly enough, the total energy content of the universe appears to be 0. So you can make the universe out of nothing, literally, and that's probably how it got made. And Alan Guth at MIT will tell you that you can make more universes in the same way. You can do a small experiment that starts a new universe. All universes, by definition, are segregated from one another. There's no causal connection between one and another. So the one problem with having, as a home hobbyist, with making a universe is that you never know whether you succeeded or not.
I just wanted to question the concept of entropy in expanding universe. Is that thought by cosmologists to still continue to occur, and are we all really going to be disintegrated at some point in the future?
The second law of thermodynamics maintains that systems run down in the long run. They become more disorderly. The law refers only to closed systems, so there's some question whether the universe approximates a closed system. But most cosmologists, I think, would say yes. As a rule, generally speaking, the universe is running down. We don't have to worry about it because there's no conceivable way that we can imagine us being around when this becomes a problem for public utilities. We're talking about 100 billion years in the future. But Freeman Dyson has done, and some other people have done some work on this, what happens when all the nuclear fuel is exhausted and an open universe keeps expanding forever. In the end, you're really up against entropy. How do you keep the show on the road? And black holes turn out to be useful. You can keep drawing energy out of black holes. And it's an interesting universe, a lightless universe of black galaxies, civilizations running on black holes. On the theoretical level, I think that there is still, however, some question whether this really is cosmologically strictly true. Most people would say, yeah, probably so. I'm going to read one of the written ones here that was handed to me, and then I'll go back to the mic if I may. Now that a Hubble telescope artifact appears to confirm an example of a gravitational lens, what research is suggested concerning existing astronomical data? The gravitational lens is a prediction of general relativity that if you have an intense gravitational source in your line of sight and a bright thing behind it, light coming from the bright thing will get bent by the gravitational field, curved space-time near that object. And if you're just in the right location, it can act like a lens. So you have a lens made of curved space. And actually, several dozen of these have been found now. And they're very useful indeed, potentially so. Where they really come in handy is if you get a variable source. There are some quasars that vary quite rapidly in brightness. Presumably, these are young galaxies near the outposts of the universe. They have black holes in the center. Black holes, for some reason, pulsate in brightness with some regularity. If you can get an image of one of these things that's doubled on either side of a gravitational lens, and so far only one has been found like this, the pulses will arrive at different times because the 2 light paths are not identical. And if you can do all the geometry, you can, in ordinary old Euclidean terms, you can find out how far it is to the quasar and how far it is to the intervening lens and so forth. And this provides an independent check on the measurement scales of the universe. So it's a fascinating field. A lot of work is going to be devoted in the next 5 or 10 years to searching for gravitational lenses. And they're equipping a dedicated telescope with a whole spaghetti of fiber optics lines. And, you line up each one on a different point of light, and they all feed CCDs, and computers, not having yet unionized themselves, work slavishly all night long on this stuff. And some more lenses, I think, will probably be found by this method. Yes?
I had a question about, when you mentioned about the expansion of the universe between galaxies, does that mean that if you were to travel in a spaceship from the Milky Way and you tried to travel to the next galaxy, does that mean with the expansion of the universe between galaxies that the longer you traveled and the faster you traveled, trying to reach the next galaxy, you would never reach the other galaxy, and you would just be actually getting farther and farther away because the universe is constantly expanding?
Not locally, between us and the next galaxy, or between here and the Virgo cluster. We're in a supercluster of galaxies. We're toward the outskirts of it. It runs on down to Virgo, which is at its center. All of Virgo is pretty much bound against expansion. The expansion is tugging Virgo a little bit apart, but the main dynamic is that Virgo is assembling itself. So in the whole history of the universe, Virgo has been trying to collapse, and the expansion has been trying to pull it apart. And there's a turnaround point. About 2/3 of the way out from Virgo, you reach galaxies like us that'll never fall into the center. We'll keep moving apart, but we're not going to move apart as fast as we would if there weren't all these galaxies gravitating either. So in terms of travel agents, just to get from here to Andromeda is not such a big deal. If you tried to go cosmologically significant distances, you would start running up against expansion, but it would be the least of your problems. Yes?
Yes, sir. I recently read a book called The Big Bang and
Yes. I'm sorry, what's the yes? Okay, thank you. Sorry, yes. Yes, I heard that, yeah. The plasma cosmology lacks a champion. There's no working cosmologist, to my knowledge, who upholds it. Until there is, it's not going to be discussed seriously. It's a little like, you say someone's got a great new golf stroke but has yet to play on the PGA circuit. You think, well, I'll wait until I see the results. The book you referred to is written by an engineer who has a theory, and I haven't examined the theory closely. Some cosmologists have. And I'm sorry, I can't give you a more positive answer.
My question's a little closer to home. You talked a lot about how our cosmology is limited basically because we have to assume that our assumptions are typical. And
one does make that assumption. Yeah, you don't have to, but we do, yeah.
Well, isn't that very similar to the fundamental attribution error? And what do you see that in as well as with our studies in psychology?
What is the fundamental attribution error?
Well, partly that we assume that others' actions are all based on internal reasons, and our actions are based more on external causes.
Well, maybe. I mean, you can violate this principle, and cosmologists do sometimes to try things out. But the universe has over 100 billion galaxies in it. Probably a lot more. The observable universe has an estimated population of 100 billion galaxies. The total universe, if inflation is correct, is a whole lot bigger than that. A cosmology that takes a map that size and says, we just happen to be in a privileged position, so things work out in a certain way, has problems, but they may not be insurmountable. Let me read a few. If the universe if it expands and contracts, how about matter? Matter stays the same. Brooklyn doesn't expand. I don't have a question, just a comment. I'm a junior in high school with very little interest in science. And you've done nothing to change. No. And and I'd like to thank you for finally making the universe interesting. Thank you for that comment. Your program, Creation of the Universe, was one of the most popular components of my high school physics. We start putting the ads in now? Is this the... Why are there currently 3 spatial dimensions? What a wonderful question. That's a subject of real inquiry. If the universe, as appears possible, began with 10 dimensions, let's say, and somehow those 10 collapsed into 3 plus 1, how come 3? Well, it could have just been chance. Maybe there are a lot of universes, and some of them are one-dimensional. So everybody lives like a subway engineer, you know, you just go in one direction, that's all that ever happens. Maybe some of them are 2-dimensional, slightly more interesting. But no one knows a particular reason why it has to be 3. Is the universe based on chaos theory, or one might add fractals? There are people who hold that fractal theory explains galaxies. Perhaps this tells us that the breaking of geometries from the pure early geometries can be found in these structures. Do you see forming a new religion which accepts the world of science but assumes a deity compatible with science? I don't know that you need a new one for that. Aren't there? It's already some. Since there's no duplication of anything in the universe, what are the chances of any living creatures anywhere else in the universe being duplicates of human beings? I would estimate that they approximate 0. Humans are very complex. How we got to be here is very complex. I don't think they're going to be just like us, except they're silver and 4 feet tall. And think that Tchaikovsky is a better composer than Bach. Now, I'll go back to the microphones. I don't want to ramble on and on here all evening. Do you want to stay for a couple of minutes and have some more questions? Okay. Let's start upstairs. Yes. It comes from a field called supersymmetry, which is an attempt to find a way to write a unified theory. That is, a set of equations that will give you the results of all interactions involving the 4 known fundamental forces of nature: gravitation, electromagnetism, weak and strong nuclear forces. One approach is to imagine higher geometries, how a physical law would work in a higher geometry, more dimensions than 4, and see if you can arrive at a result. People worked further and further up. You can imagine what a headache this is. You know, you're writing 6 and 7 dimensions. Every time you add a dimension, you know how it's like 3-dimensional chess, 4. I once talked to a physicist who spent his summer in Paris working his way all the way up to 9. And he said it was miserable. It was hot, and everyone else was having a good time. They're saying, "Why are you working so hard?" And he said, "I've got to press on, you know." He got to 9. It was unbelievably hard, and he said, "This is going nowhere," and he quit. 10 solves it. 10, suddenly things start to make sense. They also do at 24, and at nowhere else, no other dimensionality that's been encountered. So given a choice of 10 and 24, most people are tending to back 10. Yes?
When you were giving your points about the right brain and the left brain, and when you were mentioning about the hypnosis, and I think you mentioned the term was the regulator, which could be susceptible to a hypnotic suggestion, which I took to mean then would carry out an action by another side of the brain upon the end of hypnosis. In other words, you were using
the point of that example was that there's a module in the brain or a program of some sort that'll explain your actions even when it has no idea why you acted. So you've seen this. Like for instance, because the brain's complex, someone will do something violent, acting on the instinct of the lower brain, and the higher brain never got a chance to intervene. It was just happened too quickly. So the higher brain goes to work making things up. He swung first. Nobody can talk to me that way. You know, I'm sorry, dear. I didn't. You know, that's the interpreter speaking, that program. It's not that that program is influenced by hypnosis. It's that hypnotic suggestion blocks, in this example.
But where does the hypnotic suggestion work?
Well, it's a higher brain function like the interpreter.
But it can influence both sides?
Well, apparently it can block one realm of knowledge from another part of the brain, similar to cutting the brain.
And is that the only kind of way you can manipulate it? For instance, hypnotic suggestion?
No, I don't think so. I'm not an expert in hypnosis. Okay. I think you can do other things too. You can make people quack like ducks and... yeah, so anyway, I say I'm no expert.
What's the current thought on the first constructions of amino acids and proteins, and is this consistent or inconsistent with the second law of thermodynamics?
I don't know the answer to that question. It's a sort of formation of life question. It is not, in my opinion, inconsistent with the second law of thermodynamics because we have here a system into which energy is being pumped by the sun. It's also pumped by radioactive energy from inside the Earth. So lots of things that are not entropic go on Earth all the time. This meeting tonight is one of them. But I'm sorry I can't answer your question more specifically, yes.
What have your studies and observations led you to believe about the existence of God or a spiritual force in the universe? And secondarily, what are your thoughts about the evolution of the human brain and man in a spiritual dimension?
It's just too broad a question for me to answer. My thoughts and feelings about God seem to be more or less independent of this sort of thing. I've tended not to conflate them. But many people do, you know. The best story I ever heard about the question of the existence of God came from a theologian who said that a friend asked him, "Do you believe in God?" And he said, "I can answer you, but I promise that you will not understand my answer." The guy said, "Okay, what's your answer?" He said, "Yes." I'm happy to say that I don't have the expertise to answer that question. Did you have another one? Okay. No, I'm sorry. I have a few half-baked theories about the difference between how men's and women's brains operate. They are very different, you know. Neuroscientists can tell you very quickly whether a brain handed to him or her is a man's or woman's brain. And the differences are very of great interest, obviously, but also of great complexity, yes.
One of the things about the idea of the expansion of the universe that's always confused me is that the theory predicts an expansion of space.
Yes.
Space expands. And the confirmation of that theory is based on a measurement of distance, effectively, the speed of recession of distant galaxies.
Velocity and distance, yeah.
Yeah. Distance per time, a vector. If you were to measure distance by measure things by the distance between the tip of your finger and the tip of your thumb, and your body was expanding at some rate, along with everything else, how on earth can you measure that change?
That distance becomes a more and more slippery concept as you get to cosmological distances. If I'm a quasar, so I'm moving away from you 90% the velocity of light. You make a measurement today of me, you say I'm at a distance of 1 billion light years. But it took 1 billion years for the light to get to you. Meantime, I've been moving away. So I'm not 1 billion light years away from you now. You know, I was back when you took that measurement. And that's called look-back time.
But the problem with that is that the distance I'm talking about is not the distance of the galaxy, but the frequency of the light that's coming from the galaxy. That's a small distance.
Well, yeah, I'm sorry, then I don't understand your question.
Or the wavelength of the light.
Yeah. Well, the wavelength of the light is stretched out by the expansion of intervening space. That's true. Right. We call that velocity because it's an easy term to use. And it's velocity, okay. You know, it's you go there, it's gone, you know, and how it got away doesn't make a difference. But the problem with the concept of velocity is it tends to make people think of the thing's plowing through space, and that's, of course, not. It's sitting more or less stable in space as far as it's concerned. It's that the space is opening up. Let me read a couple. Here we got a couple more. And we're going to, I admire your patience, but we're going to wrap this up in about 5 minutes. Is it possible that at the far limits of the observable universe, we are looking at our own local universe as it was billions of years ago? It used to be that the answer to this question was we don't know. Now I can say that the answer is no. For that to be the case, the curvature of space would have to be so great that by now we would have been able to observe it. Either the universe is open or it's closed. The middle case between the two is flat. space is almost perfectly flat. The curvature is extremely gentle. The inflationary hypothesis explains why that might be, and that's one reason it's so popular. It also means that the universe is enormous. It's not smaller than we thought, to answer this very thoughtful question. What is outside of space? Well, now I started out by saying that you can't be outside of space. Aristotle explains that. Take it up with him. What is the probability of a technological civilization existing close enough to be contacted? I don't know. The SETI search by NASA just began. It's an attempt to explore this very question. It's criticized as unscientific. I think it is unscientific, but it's exploration. You know, the SETI search says we just don't know unless we try to find out. Frank Drake is the inspiration behind that project. Estimates that there are 10,000 technologically advanced civilizations on the air in the Milky Way galaxy right now. If that's true, we should detect a signal from one of them in something like 10 years. The expansion of the universe is inferred from the observed redshift, but what if there was some quality of light which, like tired light? Yeah, that could replicate it, but there's no physics known that would do that, so it's an ad hoc explanation. How are planets formed? Big subject and a very important one. And I'm back to the beginning. Let's have 3 more questions if there are that many, and we'll wrap up starting with Mike 3. I think, you know, entropy, the entropy god seems to be with us tonight. Entropy is not all that big a deal. If you're out on a cold, frozen night, and you got a choice between setting up a camp and having a fire and sleeping there, or just throwing yourself down on the frozen tundra, sleeping out there, you're better off to have a fire. That's what the stars are. They give everybody a campfire, which they can draw tremendous energy and beat the odds of entropy for billions of years. That's why we assume that life is to be found around those campfires. So we would expect a signal to come from close to a star and not from out in the frozen wastelands. But there are a lot of stars, you know, presumably a lot of habitats. Yes.
I've heard the theory of multiple dimensions sometimes structured as the model where each dimension would be at a right angle to another, trying to make four spatial dimensions conceivable. What do you think of that theory?
Yeah, that's the way to think about dimensions. It's easy. All you have to do is take a pencil, you know, and that's 1, and cross the pencil at right angles, and that's 2 dimensions. Cross another one at right angles, and that's 3 dimensions. Cross a 4th one at right angles, and that's 4 dimensions. And when you've got it made, bring it in to the science fair. And, thank you for that question. Yes?
I need you to clarify something. I think you said that the universe is the total set of all observable phenomena.
All potentially or actually observable phenomena, yeah.
Okay, if it's just as it's meaningless to talk about space beyond the edge of the universe, how can we talk about the early stage of the universe, like what happened in the Big Bang, before there was mind to observe it?
Because that's why the word potentially is put in there. It allowed me to weasel out of just that point. A mind comes along later and makes observations that allow it to reconstruct what happened so the Big Bang becomes an observable phenomenon. It's a phenomenon that had consequences, and this room is full of some of its consequences. All right, I promised there'd only be 3 more questions, so I apologize to those of you who are still waiting. I'll be happy to talk with you afterwards. I'd like to thank you all for coming this evening. I've had a great time. I hope you did too. Good night.